This title, I was actually surprised when I saw the announcement, because I thought, is that the title I sent in? Because the title I sent in is actually this one, but I think Brian in his wisdom realized this might reduce the size of the audience. So he, and I think it was probably a wise choice. So I will talk about understanding uncertainty in climate models a little bit in general, but I'm then going to focus on this specific topic, which is the circulation response. So I'm going to first just give an overview of the first half of the talk, which will be fairly general, and then the second half will get a little more technical. So a couple of points just to make at the beginning, and then I'll illustrate these with some slides in the next 10 or 15 minutes. So the first thing is, if you consider global aspects of climate change, these are like surface temperature and so on, these are robust. Both in the observations, robust meaning that it doesn't really matter which data set you use, it doesn't really matter how you analyze it, you're always going to get the same outcome. Both in the observations and in climate models, and I will make an emphasis on what I call physically based climate models. Of course, there might be all sorts of different models one might use, but when we talk about climate models, we usually mean models based on the laws of physics, Newton's law, first law of thermodynamics, and so on. These are the foundation of our understanding. And the main uncertainties there are how much the rate of forcing, this is basically the forcing of the climate system, will increase in the future. So for example, that involves questions like what we do on the human side in terms of mitigation option, in terms of the emissions of the greenhouse gases and so on, perhaps geoengineering. And on the other hand, it depends on what the biosphere does, because a certain amount of the carbon that we emit gets taken up by the ocean and the land, and so that's another important part of the uncertainty. So there's an uncertainty in terms of how much what we call the rate of forcing, which is really the greenhouse gas loading, will increase. So that's what's called a scenario usually in the models. You just say we're going to assume a certain scenario. And then the other big uncertainty is how much warming results from a given rate of forcing, and that's the classical question of climate sensitivity. But then when you come down to, and these are not small uncertainties, I should say, but they are, but we're working with fairly robust sort of tools and observations. On the other hand, when climate impacts will be felt at the regional scale, because that's really where, it's where we live, of course. Where, agriculture is a regional phenomenon. Flooding is a regional phenomenon. Even sea level rise is actually a regional phenomenon. And if you consider the regional aspects of climate change, which is what we're really dealing with now, they're generally not robust, either in the observations or in the models. And one of the reasons for that is that they're determined by atmospheric circulation patterns. So just in some sense, the global patterns are determined thermodynamically, if you like, and the circulation patterns are determined dynamically, meaning fluid dynamics. And these circulation patterns, just like with the butterfly effect and weather, they are chaotic. You have this chaotic variability that makes them hard to predict, and there's very long time scales. They actually vary not just on year to year, but over decadal or multi-decadal time scales. And they're strongly affected by model biases. So if you're concerned about the amount of rain and how that may change over Britain, that depends on where the jet stream is. If the jet stream is in the wrong place, the storm is going to be in the wrong place, and you don't have a meaningful prediction of how that's going to change. So the model bias problem becomes very important when you get to the regional scale. So just to illustrate this, so these are probably the three most famous global indicators of climate change. This is the surface air temperature. It's over land, which is why the increase is so large. You see it's been steadily going up. This is the global mean sea level. You see it's been steadily going up. The other indicator is Arctic sea ice, and so this is not a time series, obviously. Sea ice has a seasonal cycle. It reaches a minimum in September, and then it reaches the maximum about 6 months later. And the minimum this is the median of the minimum over 79 to 2000, is given by this pink curve here. But this was the minimum that was reached just last month, which was a new record. And so sea ice is really disappearing fast in the Arctic. So as I said, there is uncertainty in the future evolution of the rate of forcing, and you usually see that in these kind of plots. This is from the last IPCC report. This is global mean. This is not the rate of forcing, it's the global mean temperature, but still it basically is responding to the forcing, of course. And this is the past, and then this is the future, and each of these different curves corresponds to a different scenario. In other words, it's a different set of assumptions about how the rate of forcing might change in the future. And you see that there's a big range. I think we can all assume that we're not at 2,000 emissions. So basically, of this range here, there's a factor of 2 in the response. But actually, what looks like uncertainties around these are actually, so these are, what this is generated from is a large collection of models, maybe 20 or 30 models in the what's called the CMEP3 ensemble, and for the different scenarios. And what looks like an uncertainty is not really. It's a standard deviation, but there's a lot of question about what the spread of these models means. I mean, there's a sense that the models I think there's a sense the modelers never really like being outliers. So there's a sense that they want to kind of get themselves back in the middle of the pack. And so if you do what IPCC did then was do a best estimate used on expert judgment of what they regarded as the likely range of warming, and this is only greater than two-thirds. And you see that, for example, just to take the A1B here, the uncertainty range is about a factor of 2. So it's much, much bigger than this uncertainty. So this is the climate, this is the rate of forcing uncertainty, this is the climate sensitivity uncertainty. So why is there climate sensitivity? Well, the atmospheric energy balance is very complex. Solar, you've probably all seen figures like this. Solar radiation comes in, some of it gets reflected back by aerosol and by clouds, especially the cloud feedback is an important uncertainty. Some gets absorbed by the clear atmosphere. A lot gets absorbed at the surface and then comes back into the atmosphere through convection and latent heat fluxes and so on. And then there's also a radiative part involving the infrared, of which again clouds play a very important part. So it's really the clouds are the main reason for this climate, the uncertainty in the climate sensitivity. But this energy balance also varies spatially. And so these spatial variations, they lead to temperature contrasts that lead to pressure contrasts that drive winds. And it's interesting, I was, it's not easy, it's not hard finding a figure like this. Every IPCC report has this figure. You go on the web, everyone's got this figure. Much harder to find a figure of the circulation, because it's just not in people's heads as much. But once we think about regional patterns, and you may not like this one, and I thought, I should pick one over Europe at least, but I couldn't find a nice one, at least on Google. Even though all I heard about for the whole summer was where the jet stream was, and it was in the wrong place. You're very conscious of the jet stream here, but anyway, this is a North American version. Of course, in the old days, people were in the days of sailing ships, people were very conscious of winds. Now we're conscious of the jet stream because we travel by air. Anyway, so we have these circulation patterns, and the jet stream is a very important part of it. And because it's fluid dynamics, and if you know anything about fluid dynamics, you know that there's turbulence and uncertainty. We have chaos, and there's variability. So these circulation patterns exhibit internal variability. So this is, you probably heard of the North Atlantic Oscillation, perhaps. Climatologists tend to classify the variability through these empirical indices. The North Atlantic Oscillation is defined by the contrast between the surface pressure in Iceland and the Azores, the Icelandic low and the Azores high. And when there's a weak phase of this dipole, basically the jet stream gets pushed north, and you get cold and dry over Britain, and the warm, the wet weather is pushed to the south of Europe. But when this is a strong phase, the jet stream comes right into Britain, and you get lots of warm and wet weather here. So this is a well-known pattern. Now it's called, the O is for oscillation, but it's not really an oscillation. People don't really understand the mechanisms for this, but it's a topic of very active research. Well, I see Michael Gill was here. Maybe he explained it. But anyway, this is what we call a mode of variability. It's a chaotic variability in the system. And this obviously affects weather in the sense that it will set up the jet stream and then you get weather events controlled by that. So there's modes of variability, but they also vary, as I said, chaotically. So this is this North Atlantic Oscillation Index over about 150 years, and you can see it's oscillating up and down. It's got annual variations, but it's also got, I just put these in by eye, these are not these arrows, but you see it's also got kind of ups and downs over very long time scales, over many decades. As I say, it's no surprise really, it's a chaotic system, but we don't really understand all the time scales. And what this means is that over limited time scales, like our lifetime, you can get these apparent trends, and this will also affect impacts such as droughts. There's a lot of research going into predicting these variations, but how predictable they are is still unclear. And certainly, in terms of inferring a long-term trend in the record, it's very problematical. Now, but these are very important. This is work from colleagues at Reading, Ron Sutton, and Bu and Dong, and they of course, I got here in May, and it's been wet, and people said, "Oh, this is so unusual." Those must be people that have a long memory, because in fact, the weather has been pretty wet in the summer for a while now. What they noticed is that there's a relationship between the sea surface temperatures of the North Atlantic and the weather over Europe. So this is another index called the AMO. The AMO is the Atlantic Multi-Decadal Oscillation. It's one of the challenges is we don't know all the relationships between all these different modes of variability. But this is defined by the ocean temperatures, so it's really reflecting the ocean circulation. But of course, it affects the atmosphere then too. And they pointed out that the Atlantic temperatures had been warm over the last 15 years, but over the previous 30 years had been cold. So this, for example, shows the difference between the last 15 years and the 30 before that for the spring, the summer, and the fall. You see it's wet here. This is precipitation, I should say. But then it turned out that the temperatures were actually warm back in the 30s, 40s, and 50s. So if you look at the difference but going backwards, so this is past minus future, this is future minus past, you change the sign to get the right polarity. You can see that the changes in that period were very similar. These are very similar patterns. So there's quite a predictable part of the atmospheric response to these ocean temperatures, which really is important, rainfall. Now, so this is going back and forth, ups and downs, the kinds of swings up and down that we see here. This is just a different index. Of course, we expect that that things should get wetter over Britain in the summer, in the future. People expect this AMO to keep trending up, but it's hard to tell from these ups and downs. But the real question is, can we afford to wait until we really see a clear trend emerge? And these are pictures from this summer, and all the concern, of course, about rising food prices and everything. So I think this is really one of the challenges, is that things may be changing, but it's hard to see in the observations because of all this very low frequency chaos. And it's important that, because impacts of climate change will occur through extreme events. This is an example from Canada. It's totally outside my area, but I find it very interesting. This is, so I already showed that Arctic sea ice has been melting in the summertime. So that means that the Arctic coast is exposed to more open water. The Canadian government loves that because they can drill for more oil. But of course, it's got a lot of impact on ecosystems and communities. And so this is the Mackenzie Delta in the northwest part of Canada in the Arctic Sea. And so they had a big storm surge in 1999. And this is a record from lake bed sediments going back 1,000 years. And these are different biological species. I can't tell you what they are, but the ones in green are freshwater species, and the ones in red are the brackish or saltwater species. This is not a linear scale, but then zoomed up for the last 10 years here, and you can see that this change has been unmatched in over 1,000 years, and it seems to have led to an irreversible change in the ecosystems from that one event. This is, I think, how climate change will happen in many cases. So we have to worry about this. But because of this variability, it makes it very difficult to discern long-term trends in the observed record. So even if you have a shifting pattern, you may not be able to really see it in these time series if you're just looking for trends in a very simple-minded way. So this suggests you need a probabilistic approach to climate prediction. But how do you get the probabilities? We don't have enough observations generally to estimate that, so we're going to have to estimate it from models. So this is an example from the NCAR model in the US. What they're showing here is probability density functions, or likelihoods, if you like. These are likelihoods. This is a relative likelihood of a certain outcome. So the peak here is the most likely outcome of wintertime, December, January, February trends over the 55 years, 2005 to 2060. So these are trends in the Eurasian North Atlantic sector. Now, if you look at the surface temperature, and the gray is a control run without any climate change forced in the model. The red is the model forced with increasing greenhouse gases. So of course the mean of the gray must be 0 because it's a control. But you see there's a big spread here. And then what we see is a warming in the surface temperature. Now for temperature, which is thermodynamically controlled, there's a pretty clear offset. And this says that basically over 50, if you can afford to wait 55 years, you'll have a pretty clear distinction between a trend in the case of the changing climate and a trend in the unchanging climate. But when you go to this side of the thing, this is sea level pressure here, so that's a dynamically controlled feature. Now we see that these things are offset a little bit, but not a whole lot. And these are 55-year trends, and it's saying that, for example, you have about a 30%, even in the warming world, you have about a 30% chance of having a trend which is opposite to the mean trend predicted. And then when you look at the precipitation, it's controlled both by the weather patterns and the circulation, and by the temperature, because as the atmosphere gets warmer, it holds more moisture, so you expect more precipitation, all else being equal. If the circulation doesn't change, then warmer temperatures mean more precipitation. So the precipitation is actually somewhere in between, and you can see that there's a little more separation perhaps than here, but not a whole lot. So this means that we really have to have a probabilistic approach, and it could be that we don't see that the change we observe could be opposite to the average change, even over a 55-year period. So we need to work on developing, if we're going to use the models, we really need to develop reliable models. It's absolutely crucial. But the problem is the models have issues. This is also work from Reading colleagues Tim Willings and Mike Blackburn here. So this is circulation patterns. This is to show that there's a bias problem. So bias, of course, is systematic error, and that affects the predicted changes. These are the lower tropospheric. The 850 hectopascal is just above the boundary layer in the lower troposphere. Zonal wind speed. These are 4 of the leading climate models. This is the GFDL and the NCAR model from the U.S., the French model, and the Met Office model. And the contouring here shows the zonal wind speed in the climatology, the average zonal wind speed. And you can see they all have a wind speed, they all have a maximum wind, which is more or less in the right place, but the magnitude you see is very different in the 4 models. And then the contours show that the predicted changes over 100 years. So this is not subject to variability now. This is going to be a deterministic change, but you see that there's almost no correlation between these 4 models at all. So we don't have any idea how the circulation is going to change if we just look at these 4 models. And this is the bias problem, which really has a huge impact on prediction. So to recap this first part of the talk, both chaotic variability and model bias present many challenges. On the one hand, we may get serious regional impacts of climate change even before the observed trends are statistically significant, at least using the usual tools that climate scientists use. So there's a general need to move from a confidence, if you like, to a risk framework. So just to make this a little more concrete, though I won't say any more about it, but it's worth pointing out, I think, the scientific community, and it's exemplified by the journals that we publish in, it's exemplified by IPCC Working Group 1. We want to make statements with high confidence. So, highly likely, virtually certain, all these things have to be 95% confident, 90% confident, and so on. If you ask whether hurricanes in the Gulf of Mexico are going to increase, we're not confident that they will. But if you are in charge of the levees in New Orleans, and you have to worry about whether you might have to build them higher after Katrina, because climate scientists tell you that maybe sea level will rise and maybe storms will be more. You certainly have to be concerned there might be a 20% chance, let's say, of the storms getting stronger. So you don't have to have high confidence to have a very significant risk. And so there's an important, I think it's important as a community that we think about how to map the traditional statements about confidence into risk statements. So I'm interested in trying to pursue that. I'm actually talking with statistics colleagues here about that sort of thing. The other aspect is because the bias problem, we somehow need to get useful information from flawed models. We can't wait, of course, for the models to get better. That may take a long time. So people have to make decisions now, and so there's quite a community working with trying to deal with these flawed models and sort of calibrate the projections based on biases and so on. But it's difficult to do because it's not really clear how you map the biases onto predictions. But anyway, this is another large area, you could say, calibration of predictions. But ultimately, I think these models were all based on the laws of physics, which we believe and trust, and ultimately we just need better models. And so we have to get rid of some of these biases or reduce them anyway. So that's what I'm really interested in, and I'll be well, I'm interested in many things, but that's one of the things, and that's what I'll talk about in the second half of the talk. But one of the challenges here is that you think of the weather, these circulation patterns are forced by large, what are called Rossby waves of planetary scale, which are forced by mountains and by land-sea temperature contrast. We have weather systems, scales of 1,000 kilometers or so. And I think there was a belief that once that the models got the high enough spatial resolution, by which I mean that you think of a model as representing the climate or the weather of the atmosphere with a grid with a certain resolution. So let's say a typical weather forecast model might have a grid of 10 or 20 kilometers. A climate model maybe 300 kilometers generally. So that's, you represent, let's say, Britain by one grid box with that resolution. So I think it used to be, people believed that the dynamical part was kind of a solved problem. In fact, when I was getting my PhD, it seemed that so dynamics was somehow like learning Latin. It was something that you had to do. You had to know what a Rossby wave was, but all the uncertainty was about aerosols and rate of forcing and so on. But in fact, higher resolution does help, but it's not robust in the sense that it's not clear that you don't always get a better result. And maybe for that reason, centers don't do that because it's, of course, very expensive computationally. And so but I think the fact that models don't robustly get better is telling us something. It means that actually the scale of the weather systems isn't the only scale that we have to worry about. There's also smaller scales. So if I say that the model has a resolution of 300 kilometers, that means that there's a wind and the temperature and the pressure and water vapor every 300 kilometers. But there's obviously variations at smaller scales. So these are not resolved, or they're unresolved, or they're sub-grid scale, below the grid scale. So these effects are parametrized. They're represented in a parametric way that's linked to the largest scales. This is much more complicated. I think we know how to handle the resolved scales in principle, but we don't know how to handle these unresolved scales in a very straightforward way. And so the fact that there's this challenge, that these stubborn biases which persist and have persisted for a long time, suggests that they're linked to something unresolved. The problem with this is that if you have errors in these parametrized processes, they immediately will lead to errors in your winds, and that'll lead to errors in the weather systems and those feedbacks. So you get all these feedbacks, strong dynamical feedbacks within the climate system that really obscure the cause of the error. So the challenge is to somehow break that, because it is a very nonlinear system. So the challenge, if you want to diagnose the cause of the errors, is to break that feedback loop somehow. So that's what I'm going to talk about a little bit in the second half. So what is a parameterized process? Well, as I said, it's going to be a process that's below the grid scale. And the one I'll actually talk about exclusively here will be mountain waves. There's also other very important parameterized processes are boundary layers, convection clouds, But mountain waves are an important process. So here's a mountain wave. Well, here's a cartoon of a mountain wave. You have flow over mountains, of course, that induces these ups and downs, just as it would in water. I think you're all familiar with waves on water. Those are also, those are gravity waves. There's also gravity waves, not gravitational waves, by the way, if you're from physics. There's also gravity waves internal to the atmosphere and the ocean that have to do with the stratification. So it's not quite as intuitive as the wave on the surface of water, but it's exactly the same process. It's just the difference is those waves can propagate in the vertical. So we see mountain waves every time that we see this kind of cloud pattern. These waves propagate up, and just like corrugations on a road would slow down the traffic, these waves provide a frictional effect on the waves, on the winds aloft. So we call that gravity wave drag. It's a frictional effect. And this is, as I say, sub-grid scale in the sense that these processes are happening at grid scales below the model. And it's not well constrained observationally. Of course, we know where the mountains are, but we don't know, but there's a lot of details in how the waves get generated and how much propagates up. And it's a very intermittent process, very small scale. We don't have a lot of constraints. So when people represent these in the model, they don't have a lot of guidance from observations. Okay, so we'll come back to mountain waves a couple times. So I mentioned the NAO. Well, in the winter season, it turns out that the stratosphere is very active. And the stratosphere, as Brian said, is above about 10 kilometers, at least at these latitudes. So in the stratosphere, there's a vortex, a big vortical flow around the cold stratosphere, because you have an absence of sunlight in the wintertime, and you get this strong circulation around it called a vortex. And it turns out that this vortex couples with the surface, and it couples through the effect of weather systems. So this is now called, so the NEO is defined by the surface pressure, but this is called the northern annular mode. It used to be called the Arctic oscillation. The reason it's called that is because it's got this annular type structure around the pole. And it turns out it co-varies with the surface. And so when you have a positive phase of the, so I'll use this term a lot, this NAM. When you have a positive phase of this NAM, it means you've got a very strong flow up in the stratosphere. And that means that the winds over, say, the latitudes relevant to Britain are very, very strong, and you got the storms tracking in here. Whereas if you have a less cold stratosphere and a weaker vortex, then you get this phase where the main storms are pushed into southern Europe. It really amuses me to see this little sun over Britain. I just find that hard to believe. So there's this coupled aspect to the whole variability, and it turns out that variability in the stratosphere seems to influence the surface circulation. This is a plot, this is all observations of these northern annular mode indices. So basically you plot, just like when I showed the NAO, the index goes up and down. You're in the positive or negative phase. And you can see that if you just composite, so what's done here is you take all the observations, and when you get a very weak vortex, a very strong phase, negative phase of this NAM, then you mark it, and then you make a composite. And in the historical record, there's been 18 of these very weak events, and you can see that if there's a weak vortex in the stratosphere, it lasts about a month in the middle stratosphere, and it lasts about 2 months in the lower stratosphere, and it seems to influence the troposphere as well. On the other hand, if you have a strong vortex, it's the same thing in reverse. So what this shows is that there's actually some influence here, and that you actually have a control on the weather systems over a couple of months. Of course, the variability is coming from below anyway. The vortex is disturbed by weather systems and waves propagating up from below. But the disturbances in the troposphere get quite strongly damped by friction and by heat exchange with the ocean and so on. In the stratosphere, it's quite quiet, and the radiative timescales are very long. So there's actually a lot of potential memory, subseasonal memory in the stratosphere, and that's what gives the persistence of this anomaly, and you can see it really affects the surface. So it's been known for a long time from these sort of plots that this is possible, and actually models have begun to get that right, and this is a result from our Canadian models, the Canadian Middle Hemisphere model it's called, from Michael Sigmund at Toronto. What's shown here is observations of mean sea level pressure, that's the contours, and precipitation, which is the color shading following the most dramatic events, which are called stratospheric sudden warmings, of which is about 20 in the observational record here. So this is the surface conditions between 16 and 60 days after a sudden warming happens. So it'd be like this period through here. And this is the model. If you take the model and you make a forecast after the sudden warming, you get a lot of this. These are anomalies, I should say. This is not surface conditions. This is the departure from the climatology that you would expect. And you can see that it's not perfect, but there's a lot of skill in this. And so if you've got models that can actually do this, it means it opens the door to using these forecasts as a test for the models. The problem is we can't test a climate prediction because we can't wait for that to happen. But you can test, for example, perhaps some shorter lead time forecasts like this. So this sort of thing provides an excellent test of climate models, and people are getting interested in doing this. But this effect of the stratosphere on the troposphere extends to not just subseasonal, but extends to interannual variability. Now this is also winter time, and what's plotted here are time series from 1971, I guess, to 2000 of this, again, this Northern Annular Mode Index, NAM index, but at the surface now. And the black curve shows the observations. So you can see that just like with the NAO, the black curve is going up and going down and going up and down, so it's oscillating around. What's shown here in the red is an ensemble of climate models with some spread about it, where you just impose the observed sea surface temperatures. And I should point out, the Sutton and Dong paper was about what was not for the winter time, it's for the seasons apart from winter, where the sea surface temperatures seem to exert some control. In the winter time, they seem to exert no control because of the influence, I think, of this NAM. And you can see that the model ensemble in red just doesn't really follow the observations at all. There's a correlation of 0.35 here. But if you constrain, this is historical, if you constrain the model to follow the observations in the stratosphere, poleward of 25 north, this is so that it's not an effect of the quasi-biennial oscillation, which is a technical point. So it's constrained by the sea surface temperatures and by the stratosphere. Then you get almost a perfect reproducibility. So that's telling you that if you can get the stratosphere right, then you'll get the surface right. That's because the stratosphere is the upper boundary condition. So mathematicians know the boundary conditions are very important. And if you don't get the boundary conditions right, you won't solve the problem correctly. So that's important for things like these decadal variability. But it also appears to be relevant on longer time scales. So this is for climate change. This is again from Michael Sigmund's work actually with the CMEM. What this is the mean sea level response to double CO2. This is over the Arctic here. And you can see that the results are very different. Well, what's different with these two runs? They have different settings of a parameter in the mountain wave or the orographic gravity wave drag scheme, both of which are plausible. They're within a plausible range. And you can see that the answer changes completely depending on this orographic gravity wave drag. And they track this down, and it turns out to be through the control of the lower stratospheric winds, which control the weather systems. So there's a lot of sensitivity. So gravity wave drag comes in. This is an example of the systematic, the sort of structural uncertainty because of the systematic errors in models. And even if you look at the models so you might say, okay, well, we know that the stratosphere is important. So let's look at the models that have a good stratosphere. So these are the SPARC models or the CCMVAL models. And this is predictions in the past and the future. So from the 1960 to 2100, in the wintertime, December, January, February, in the spring, March, April, May, but you can see it's a bit of a mess. And some models show a big trend in the winter, some don't. So there's no consistency here. And if you look at individual runs, you see there's a lot of ups and downs within each simulation. So there really is an issue here. It's going to be very hard to say what's going to happen on the basis of these models unless we can somehow deal with these errors. And I'm convinced that they've got a lot to do with the gravity wave drag. Okay, so the second topic, that was on the northern hemisphere. I just want to touch on the southern hemisphere as another example. So you may or may not know that actually the climate change in the southern hemisphere has really mainly been detected in the summertime, and it's actually got nothing to do with greenhouse gases at all. It's to do with the ozone hole. The ozone hole has been a huge perturbation to the stratosphere. And when you lose ozone, you cool the stratosphere. That extends the winter season essentially, and that has, through this same downward coupling mechanism I talked about, affects the surface. So it's like this, like the northern angular mode, but there's a southern angular mode, and if you perturb it in the stratosphere, you get a response in the troposphere. These are observations. This is linear trends from, I think, 1970 up to 2000 of mid-tropospheric geopotential height, but this is maybe the surface temperature and winds. You can see the main thing is you get a speed up of the vortex around Antarctica. This has implications, by the way, for ocean circulation, heat uptake, carbon uptake, possibly. This is a model if you force it with an ozone hole, and you get very similar pattern. So if the ozone hole has led to big changes in the past, then we expect the ozone hole will go away over the next 50 years because of the control on CFCs. It'll take a long time, though. It's about 50 years. Then we expect that the sign will turn around. And that means that ozone recovery would weaken or possibly reverse the SAM trends. I should say that climate model predictions are that increasing CO2 will also strengthen the surface winds. So in the past, they were acting in the same direction. In the future, they'll be acting in opposite directions. So this is some from the IPCC models last time around, which didn't impose an ozone recovery, and these are projections of the wind trends in the southern summer over 50 years, and you see a great big increase of the surface winds at 60 south. But if you have an ozone hole in there, then the recovery period is basically nothing happening. So it's an important effect. This is work from our Canadian model led by Charles McLandris. The effects actually are not just on the surface winds. They're actually on the Hadley cell boundaries. This is the edge of the tropics, essentially, the 30 degrees or so. And it turns out that the ozone hole has an effect on the southern edge of the Hadley cell, which has implications, of course, for descent of dry air and so on. These are little complicated plots, but what's shown on the left is trends per decade, degrees per decade, so it's latitudinal shift over the past when the ozone hole was developing and over the future where the ozone hole is recovering. The blue dots show various kinds of models without an ozone hole in them, and you can see that the trends are the same past and future. These other dots and things show models with an ozone hole in them, and you see that there's a greater trend in the past and there's a reversal in the future. Same thing if you look at precipitation, you get the same kind of a pattern here, that there's the difference between this bubble and this bubble is the effect of the ozone hole, and this bubble and this bubble is the effect of ozone recovery. So you have to worry about this if you're gonna get things right, and this, as I said, it's important for Southern Ocean heat uptake and carbon uptake. Potentially also people have claimed for ice sheet stability. But the models have biases, and gravity wave comes in again. This is a result from former student Tiffany Shaw, who this is the surface again, the mean sea level response to the ozone hole. This is with a lid that's at about 95 kilometers. So we think that all the physics is right, or at least if the model's right, we're doing this right. But then this is a bit technical. But if you don't conserve momentum flux in the gravity wave drag scheme, which is typically actually the case with a lid that's more in the middle stratosphere, you lose the significance, which is a shading. You really lose a lot of the effect of the surface on the surface of the ozone hole. So how you treat the gravity wave drag scheme is important. You can see probably the major bias is that the models said that as the sun comes up in the summertime, the polar regions heat up and the winds change from westerly to easterly, which is to say eastward to westward. So the transition to easterlies is the beginning of the summer, if you like. And in the observations, it's this black curve that comes down in time over the course of about a month. But you can see the models are almost all late. So, but this will affect the surface response. And so how much does this model bias affect all these projections of the surface response? So I won't answer that question, but what's the reason for this bias? And it occurred to me that all the models must be doing something wrong for the same reason. And the thing that all these models have in common is they don't have any mountain wave drag at about 60 south, which is the maximum of the jet. This is a version of the model with data assimilation, which is where you bring in observations and make a short-term forecast for 6 hours and correct and make a short-term forecast. And from the increments from the data assimilation, you can infer basically what the missing force is that your model doesn't have. And you see there's a negative force here in the upper stratosphere that comes down as the winds change. And so this looks like a mountain wave drag, because it's at least a very low phase speed wave. If you look at the mountain wave drag in the model, there's this big zero right at 60 south. That's because in the model it's ocean at 60 south. But actually there are mountainous islands that provide a lot of gravity waves in observations that are just not represented in the climate models. And also gravity waves propagate latitudinally, not just vertically. So there's reasons to believe that there should be gravity wave drag in this gap here. When we put something in, we actually get the right kind of response. So I think you can look at these short-term forecasts and try to constrain things. And again, I think it's worth thinking about the orographic gravity wave drag. I'm afraid I'm going to have to skip the last. I worked so long on this figure. So there's a former Imperial student, Isla Simpson, who was a postdoc with me. She's now at Lamont. And she was looking at timescales of these variability. But it's a complicated topic, and so I thought I would illustrate it with a spring, and the idea that if you have a damp spring and a forcing, that the displacement of the spring is it gets greater if you have longer timescales. There's been a lot of work on timescales, but I think I just don't have time to talk about that. But she's been looking at trying to use constraints on the model to really see where this long timescales come from, because if the timescales are too long, then that means that there's going to be a bias. So it's a bias in the variability rather than in the mean, and she's been, again, using this, but I'm afraid I can't. I just ran out of time there. So finally, let me say that scientific interest is turning really from the detection of climate change, which has really been the big problem for the last 10 or 15 years, to the prediction of its regional impacts. And these impacts are controlled by circulation patterns. And these circulation patterns are fluid dynamical. We have turbulence in fluids, and they will have very large variability on these very long time scales, multi-decadal time scales, chaotic, so you can't just fit some sort of simple sinusoid to it. As a result, the observed trends are generally not robust statistically. But this doesn't mean that climate change is not real. It doesn't mean that the risks aren't there. Climate change will be felt through these extreme states. So we somehow have to deal with this fact that the observational record does not provide a lot of basis for determining what's going to happen in the future. So in the end, physically based climate models based on the laws of physics will have to be the basis for prediction. But these models exhibit significant biases in circulation patterns and the variability. And if you look at the predicted changes over long term, say in the future, they exhibit large spread, and these are almost certainly related. So we need to remove model biases somehow. As I said, it's likely to involve these parameterized subgrid scale processes and how those feed back on the circulation. And as I've indicated with a couple of examples, progress can be made by trying to break the feedback loops which confound the model errors, and I think that's going to be a fruitful way forward. Thank you very much.
I really wanted to talk about your first slide of your first graph, which was the rise of temperature. Because as you know, there is still, I'm speaking partly as a political person, the temperature over the land and the sea has been showing this flat for the last 12 years, which causes politicians in various countries to say, therefore, we can ignore climate change. But the point is the temperature over the land areas. Now, I wasn't quite sure whether that was a land area, because that shows the flattening.
Well,
it has been rising, and the Met Office still is the only place in the world which actually puts on its front page of its website the fact that the temperature over the land areas is rising. And it is, the IPCC executive summary always puts the land and the sea, which of course causes great consternation to politicians. Yeah. And that is still the situation. So I just, that's the PR aspect. What I just want to say about your orography, which is when I'm a serious scientist, I work on that. And as you know, the British Antarctic Survey did very, very detailed studies, and you have what we call a low-level explanation of why you get the highest temperature rise in the world, 3 degrees in 30 years, just because you divert these flows due to the Coriolis effects over that mountain, which of course is not well represented in the current model. But you should talk to the British Antarctic Survey, who are studying this in huge detail. Thank you very much.
Hi, thanks for a really interesting talk. The elephant in the room for me are the things that you didn't talk about that are not in the models. And I guess the main one is the biosphere's response to warming. And so you haven't talked about the fact that actually carbon uptake might become carbon release.
Right.
And also you didn't talk about the changes to ocean circulation. So what factors do they play?
Ocean, of course, has, I guess, two aspects. One is that it has a mean aspect in the sense of some of the warming will go into the ocean. It has to go into the ocean. And actually, one of the potential explanations of this flattening is that the heat has been taken up by the ocean rather than the atmosphere, mainly over the last 10 years. But of course, it's also very important for the variability part because the ocean has its own aspect of variability. The kind of classic picture, I guess, like I could be corrected by someone like Ted Johnson here, but I think the classical picture is the ocean is basically it's a stable medium because it's heated from above, not below. So the only way that the ocean is going to evolve is if you force it somehow, and that's going to be with the wind and so from the atmosphere. So the atmosphere is the unstable part of the system. The ocean is a stable part, but still that doesn't mean it doesn't have very long time scales, and those long time scales may not be totally predictable. Just because something is stable doesn't mean it's necessarily predictable. Yes. Right. I mean, it will be unstable on short time scales in the sense that the Gulf Stream is unstable and this sort of thing. But I guess I just mean that it's well, I shouldn't. It will certainly couple with the atmosphere. It doesn't necessarily make the whole system more. It doesn't necessarily make the system more unstable, but I guess it would make the system certainly have more variability. That's for sure. And so a lot. And we don't really, anything on the decadal time scale is almost certain to be unless it's forced by solar variability or something. It's going to or volcanoes. It's going to have to be the ocean. It's the only thing in the system with that kind of memory. We don't really know all the time scales in the ocean. I mean, there's some very long time scales in the ocean. So that is an important part, and actually, I guess another part of some of this spread may come from drift in the ocean part of the model too. That's sort of the technical point.
I'd like to ask a question about the last sentence on your last slide. And in particular, if you'd tell us a little more about the, can you give us a bit more information about what you mean, or how an example of what breaking the feedback loops that confound model error and obscure model error, and then having done that, if you would also say, just given that these model errors do couple back, you'd sort of think eventually that the models could have zeroth order errors in even the global properties. Did you have an idea of what the time scales for that to happen might be? How long? But I'm actually more interested in. I mean, I think the two questions are actually related.
Okay. So I mean, I think just to take this case, you're looking. So I probably dashed over this too quickly. What you're looking at here is you take a climate model and you basically constrain it to the observed state of the atmosphere through this data assimilation process, and then you make a forecast. And then after 6 hours, you look at the new state of the atmosphere, you look at the mismatch between the model and the forecast, and you adjust the model the observations of the forecast, and you adjust the model to be more accurate, and then you make another forecast. That's the basis of weather prediction. Now, if the model was a perfect model, the errors would just be from the butterfly effect, and the average error would be zero. It would just be sometimes this way, sometimes that way. But if you look at the average adjustment, here it's non-zero. So that means there's some kind of bias. And because you've constrained the model to the observed state of the atmosphere, it means that the winds, that those large-scale winds are right, and these Rossby waves, the large-scale patterns are right as well. So there's no error in that part of the system. And the only error that can grow on a 6-hour time scale is going to be this parameterized process, because it's a very fast process. So you're breaking the feedback loop because you're not allowing the error in the gravity waves to affect the wind, which then feeds back on everything else. So the feedbacks are important because this example for the Arctic was totally, this one here, the effect of on the surface isn't coming directly from the gravity wave drag. It's coming from the effect of the gravity wave drag on the winds and then the feedback from that. So I'm not saying the feedbacks aren't important, but to figure out that here we know it's the gravity wave drag because that's what was changed in the model. But to infer an error is very hard. But when you constrain the model by the observations, you're sort of breaking that feedback because it can't occur in 6 hours. It's just the time scales of the resolve motions are more like days. So that's the sort of example. Now, in terms of how long it'll take us to get better models, I don't think I should guess on that.
You were talking a lot about the gravity wave, like the parameterization of the gravity wave drag, which is something which is not resolved by the model because the spatial scale of the model is so big, so that's why you got to parameterize it. So don't you run into the risk of just using the gravity wave drag as another tuning parameter because, such as you use clouds as a tuning parameter, for instance, because you can't resolve them as well. How much do you see the risk in trying to get too many substrate processes with too many parameterizations that in the end you just try to tune against each other?
Yeah, well, yeah, that's a very good question. I mean, to some extent, tuning a piano is a good thing. So tuning isn't necessarily a wrong thing to do. And if you have a set of a parameter range that you know from basic physical principles or from idealized experiments or fluid or laboratory experiments or something, and then you want to constrain that from observations, there's nothing necessarily wrong with that. The problem is you want to make sure it's for the right reason, and you certainly don't want to tune to fit something and then say that the ability to fit that thing is a test of the model. It's certainly not. But that's why this kind of thing is good, because we're not trying to tune the orographic gradient drag to correct surface bias. We're actually trying to infer it from these short-term forecasts. That's an independent piece of information. And there's actually more sophisticated ways than if you find that there's a drag, you can try to infer what the errors in the parameters are. So I think the idea of using weather forecasts or perhaps seasonal forecasts, but anyway, some kind of short-term forecast to determine these parameters is a very promising area that's totally independent. I think that gets us out. It is still a tuning, but I think it's a tuning that's the right sort of tuning.
Yes, up here.
I'm an engineer, a water engineer. I'm not really into climate science, but the reason I'm here, I was more interested in the mathematical part of how we deal with the uncertainty in the models. Because, as water engineers, we get output from climate models to use in our hydrological models. And you mentioned something that kind of gave me, I would call it a scare, that the variability in the climate models is not statistically significant. Am I right with that?
Oh, I'm just saying that if you look at time series over a certain period of time, like 50 years or something, if I
No, you
correctly.
mentioned a lot of things that are changing, but you said something that the variability somewhere is not statistically significant.
Well, what I meant, I think, was that a trend in a time series, one realization over a particular length of time, let's say 50 years, may not be significant. So I'm saying if you take a model as your truth, which it's always good to test something on the model first, because if it doesn't work for the model when you know the answer, then it won't work for the real atmosphere, for the comparison with the real atmosphere. And so you can certainly get cases where, like the case I showed with these PDFs, where there's really a shift going on. You can see that, but any significance test of the whole PDF will show you that. But if you just take one realization, because the climate system will only have one realization, you would never be able to infer it from that. So that's what I meant.
Okay. What my question was really is that I thought I was getting the impression is that that you're saying that the statistics is not good enough to show you not good in describing the uncertainty in your.
Yeah. What I mean, I guess, and I should say that the statistics that are they're often used in climate science. I think there's definitely scope to improve the kinds of statistical methods that are used. People in climate science generally don't have a lot of statistical training, like myself. They come from physics or even math backgrounds. Math and stats are different fields, aren't they? And so we tend to use, I think, what are regarded as pretty old-fashioned methods, and that's sort of that's what you need to use if you want to get published, because that's what the reviewers are comfortable with, and so on. So I think there must be room to do better, and we somehow have to get more information out of this time series. But I guess I'm just saying that the typical kind of, let's see if we can see something really emerge above the noise in a time series, that may not. By the time that happens, it may be much too late.
Okay, then secondly or thirdly is Have you investigated how to because you mentioned something, we have to move away or combine confidence versus risk in your analysis. So I'm wondering now, if you want to transfer or to understand this uncertainty in the model direct to the product or to the model output like temperature, like sea level rise, and you want to describe the relationship between the uncertainty and the variation in the output. You're with me there. So I'm just wondering, since you kind of don't trust the statistics so much.
It's not that I don't. It's just all I mean is that I think this example is maybe the one. So in this case, what we have is we have a whole ensemble of models. You know, I don't know how many different copies of the model that are run, 50 or something, and you can get a distribution. Okay, we don't know if this is accurate in terms of the real atmosphere, but at least you can do experiment, you can do tests in the model world. And so these are these are all very clear shifts, right? If you have all the data, the problem is that in the observations we'll only have one of these, one example. So we don't have all the information that we need. And I guess for a statistician they would say that really it's a problem of probability, but we only have single realizations, and the models only produce single realizations, really. You can sometimes generate these things, but the models are not really probabilistic. So I wouldn't want to say that the statistics are inadequate. I'm just saying that there is a challenge that we're dealing with time series that go up and down, and yet these so it's going to be very hard to, if you just treat this as a time series without any other information, it seems to me it's going to be very hard for you to necessarily conclude that it wouldn't just go down again. And yet, if there is something happening, we're going to wind up with flooding. So we have to somehow deal with that aspect, that it's the tail of the distribution here that might be really important. Like, like let's say over here or something. But you're not necessarily going to see that, because a trend depends on the order that things happen in. Maybe that's the simplest way to say it. Maybe you're getting more events that are intense, but if they happen in the 2020s and not in the 2040s, the trend's going to go the wrong way. So trends are very noisy kinds of things.
But can I add on to that? You said about getting useful information from flawed models. I mean,
oh, yes.
So this is saying we only have one realization compared with this. But how about the useful information from flawed models?
Well, so I guess I need to look into this more, but I think the Met Office did their climate assessment that was using some sort of Bayesian approach to try to deal with those flaws, and I can't comment on that, but I'm curious about what was done. But I can imagine, and I am interested, I know that in some cases there are some examples where there's a clear link between a bias in the model and the spread in the predictions. In other words, you know a model has a certain bias, and you take all these 20 different models, 30 different models, and you look at the bias in the observable part of the system, say in the seasonal cycle or something like that, and the prediction of how much things are going to change in the future, and you find that they lie on a straight line. And you understand why that's the case, because there's some basic physical mechanism and it all makes sense. Then you would have a reason, then you can calibrate that prediction. There's a couple of examples like that, but there's not many, and I don't know, how many of those we can find. But if you could find those sort of things, of course, then you do have a basis to try to use the flawed model. But otherwise, I don't know how you do it.
So Ted, you've given a very nice talk on uncertainties in models, focusing on subgrid scale processes, and a lovely example of how you can improve gravity wave drag and thereby improve the representation of circulations in the atmosphere. So do you think that in the end all we need is higher and higher resolution models, and then we'll be able to resolve all the processes, and then that's the answer?
Well, in terms of so it depends on the kind of uncertainty, of course. There's always the uncertainties that we won't know about, like the future forcings, and the biosphere will be more difficult not to crack. But I think if we believe in the laws of physics, we do have to believe that as we get, in principle, as you have a better representation of things, you will do better. On the other hand, it's not clear that there's really a convergence. That's not obvious. Things do get more energetic at the small scales, right? And so there's, mathematicians could think about this actually. It could be that the optimal because there is a transition from the kind of, let's say the weather scales, and then at about 80, what is it, about 100 kilometers or so actually, if you resolve the thing, then you get into a mesoscale spectrum, which is very energetic, minus 5/3 spectrum actually, but at large scales. It's not obvious that that's a good place to be truncating, and maybe the better thing is to really resolve these weather systems and then only parameterize and not try to get into this other range. But of course, the weather models have been getting into that range, so we do have some experience from them. You know, I'm sorry. The answer might be yes in principle, but you know, how far do we have to go? The people that work on aerosol process. I mean, I asked some Graham Feingold, a very famous cloud guy. He said, you know, what resolution do we need before you think we would believe models? And he said, without batting an eyelid, 10 centimeters, and he was absolutely serious. So, you know, if the question is, if we're talking about a practical answer to the question, I think we can't wait for that, and we have to work with and there could be good theoretical reasons actually to try to parameterize the really stochastic parts of the process.
As you say, we can't wait for all these things to be sorted. But Ted, I want to thank you on behalf of everyone for taking us into this realm where fluid mechanics starts to become dominant again, the circulation that actually gives us the climate variability and change at a point where we actually live. And thank you very much for such an interesting talk.
Thank you.